We continue the stochastic processes playlist as we continue to look at renewal processes. And in this particular video, we turn to renewal equation. We came across the concept of renewal equation in the first video as we introduced renewal processes. So here we're looking at it in some more depth. So renewal equation. So first of all, a refresher on renewal processes. We said that a renewal process models repeated events occurring over time and let x1, x2 up to x3 be independent and identically distributed inter-arrival times. Then we define the arrival times as Sn equals x1 plus x2 plus all of that up to xn, such that the first arrival time is x1, while the second arrival time is x1 plus x2, the third arrival time is x1 plus x2 plus x3, and so on and so forth. Then we define the counting process, whether number of arrivals or number of calls received or whatever it is you are modeling, to now be n of t, which is the maximum of the possible n's we have for Sn less than or equal to the time allotted. All right, or any time t allotted. So the interpretation is that n of t is the number of renewals up to time t. So, and we also saw that such renewals could be maybe replacing bulbs or customers arriving in a queue, or calls, getting to a call center and things like that. Then we talk about the renewal function, which we also saw in the last video. The renewal function is defined simply as m of t, and that is the expected value of n of t. So, and for a Poisson process, like we saw the other time, the expected value of n of t for a Poisson process is simply the parameter lambda times t, that's the arrival rate times time. Okay, so it then represents the expected number of renewals by time t. Just like arrival rate times time simply gives us the number of arrivals, right? So that is expected value of n of t. Then we'd go on to talk about the renewal equation for which on which this video actually focuses. So renewal equation, let f of t be the cumulative distribution function of inter-arrival times. So the renewal function satisfies m of t equals f of t plus integral from 0 to t of m of t minus x dfx. If a density f of x actually does exist, then we have that m of t is equal to f of t plus integral from 0 to t of m into t minus x. Then this dfx now then we can rewrite dfx as f of x dx. So if a density function f of x does exist for the situation we are considering. So the intuition here is that the equation is based on conditioning on the first renewal. So first renewal occurs at time x less than or equal to t, and the remaining expected renewals occur at m of t minus x, so that either the first renewal happens by t or it happens at x and the process restarts. And this gives a recursive structure like that. So then we talk about the renewal density. So if we define u of t to be d dt of m of t, of course, m of t is already given as the is the renewal function, right? So the renewal density is given as the rate of change of the renewal function m of t, which is assigned u of t. Then we can say that u of t then is f of t plus integral from 0 to t of u into t minus x f of x dx. And this is another form of the renewal equation. So we can express the renewal equation as the equations we saw before as a renewal density u of t like this, which is the rate of change of the original m of t. So then we talk about Laplace transform solution. So we can actually solve the renewal function m of t using Laplace formula, using Laplace transform. In case you don't know so much about Laplace transform, you can check on my channel. I have a whole playlist on Laplace transforms. So just go to my channel and of course you look at, go to my channel like this, and then you can see, click on playlists, and from playlist you can make your way to Laplace transforms. It is actually part of the differential equations playlist, but I also made sure to separate it so that I have 21 videos like this. So that's talking about the Laplace transform. So yeah, so that gives you an in-depth attack on Laplace transform, so you can actually get a deep understanding of all of that. All right, so you can use the Laplace transform to solve for m of t, right? So we have m m tilde s to be the Laplace of m of t, and f tilde s to be Laplace of f of t. And then we know that m tilde s is the same thing as f tilde s over s into 1 minus f tilde s. So this converts the integral equation into an algebra, and that's the essence of what Laplace does, right? So you get to convert an integral equation into an algebra that can be easily solved, and then convert later to something corresponding to the original thing you had. So let xi be exponentially distributed with parameter lambda, and then n of t follows Poisson distribution with parameter lambda t. And for Poisson process, we know that m of t is lambda t, right? And that's what we have for an exponential interarrival. So m of t is lambda t, and that clearly is Poisson. Then what if you have a deterministic interval, say xi is c, right? Xi is c, whether it is x1 it is c, x2 is c. So it means that people arrive within a specified I mean, we can think about this as a system where you already have appointments to come at a particular time. So maybe people are allowed to come every 30 minutes. I mean, I've experienced this, maybe going to some embassies or going for a dental check and things like that. So everybody, people come after a fixed duration of time. So that is deterministic. So in that case, we know that we can say n of t is t over c, and of course that corresponds. So that's like some uniform distribution. And in that case, when you have uniform distribution like that, n of t and m of t are the same, and you have the floor of t over c, the list of the value of t over c, you know. So, and of course, that takes us to the uniform distribution proper. So if we let xi be uniformly distributed between 0 and 1, then we can say f of x is 1. The probability density is 1, and that's between 0 and 1. So the renewal equation then becomes that m of t is f of t plus integral from 0 to the minimum between t and 1 of m into t minus x dx, where f of t, the big F of t now, is t when t is less than or equal to 1, and it is 1 when t is greater than 1. And that's what happens for uniform distribution. So, and then we can simulate this using Python code as we have right here. So here you take t to be 5 and change in t. That small change is 0.01, and you get the renewal function for uniform over 0, 1 like this. So as time progresses, just have that that's plot sloping rightwards, sloping upwards from left to right like that, and you have m of t against time like that. You have the renewal function against time for uniform distribution 0 to 1. And then we have the renewal theorem, which we also came across in the last video. And this is a very simple concept that give if we let the mu, which is mean, to be expected value of x, which is standard definition for expectation in probability, right? Then we can say that the limit as t tends to infinity for m of t over t is actually 1 over mu. That's the inverse of the expected value, or if you like, the mean. So this gives long run rate of renewals. So that's why in the long run, in a renewal process, the renewal function approaches the number of arrivals would be 1 over mu. So this gives the long run rate of renewals. So you have an example for xi that is uniformly distributed from 0 to 1. Of course, we know the mean is 1 over 2 because that will be 0 plus 1, 1 divided by 2. That's why that's 1 over 2. Thus, now m of t over t as t goes to infinity will be the inverse of 1 over 2, which is simply 2. That's 1 divided by 1 over 2, which is just 2, like that. That's what the renewal theorem says. And of course, we have that kind of thing here. So you have taken the ratio m starting from 1 to, time 1 to infinity. So for the top, and time 1 to infinity for time m of 1, because this is m of t for sure. So m starting from 1 to infinity and t starting from 1 to infinity. And then we try to do the plot, right? So we are plotting t of 1 against this ratio of the two. And if you do that, you discover that this one that is supposed to be 1 over 2, right? So you see that the as time passes, the ratio of m of t over t, you know, it's moving closer and closer to 2.0 like that. And that is the concept of the renewal theorem. So in summary, we have that the renewal equation m of t equals f of t plus integral from 0 to t of m into t minus x dfx. We have key ideas like the recursive structure, convolutional integral, and the long run rate, which is 1 over the expected value of x. And we have applications of renewal processes in reliability theory, or if you like, reliability engineering. You have it in queuing systems, maintenance models, like maintaining a machine or replacing bulbs and things like that, or even inventory control, like you have a supermarket, and as people buy stuff, you have to restock and all that. So that takes us to practice problems here. So let x1, x2 be independent and identically distributed into arrival terms with mean mu. Define n of t and then show that n of t is a counting process. Okay, prove that n of t is greater than or equal to n. Implies that Sn is less than t. Then show that m of t is expected value of n of t is non-decreasing in t. Then explain why m of 0 is 0. All of that. So you have the renewal equation. So starting from conditioning on x at 1, derive this, then show that if f has density f, then you can get this. Prove that the renewal equation is convolution equation. So all these proofs, if you're interested in any of this, try them. And if you need help, you can let me know in the comment section, either on Facebook or on YouTube. Then I might be able to make a separate video to address these ones. So you have the special distributions, the exponential, and all of that, or a deterministic case like we saw in the notes already. Then we have using Laplace transform to solve these problems. And then you have the renewal theorem, which is very simple, that the limit of m of t over t as t tends to infinity is 1 over mu. So that means that the number of arrivals you would get at the end of the day will be very close to 1 over the expected value of x. Okay, so you have all that. Then we actually did this in the course of the lecture. For xi uniformly distributed from 0 to 1, you want to verify that m of t over t approaches to. So for xi, which is exponential with exponentially distributed with parameter lambda, you want to verify this theorem. Then we have the numerical or applied side. Write a numerical scheme to approximate this. Of course, maybe Laplace may be able to do this, or any other method that you can use to estimate an integral thing like trapezoidal, because we have an integral part of this. Then simulate a renewal process using Python and estimate m of t empirically. That was the kind of thing we did before. Then compute simulated m of t and theoretical m of t for exponential interarrival times. We did this kind of thing in the last video, so you want to check that up, especially the Python code for that. Okay, so with this, we come to the end of this interesting video talking about renewal equations in particular. Let me know how helpful this is for you. And if there's something else let me to try out, feel very free to let me know. If you have subscribed already, I thank you very much. If you haven't subscribed, why not go ahead and subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of the channel by clicking on join. That gives you special privileges like getting to some videos first or seeing some videos exclusively. And of course, we can hang out together to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, whatever. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.